Greetings and welcome. In today's video, we're going to talk about analyzing the graphs of quadratic functions. So specifically, we're talking about parabolas, where their vertex is, where the axis of symmetry is, and some general things that we'll be able to gather from it. Currently, we know how to write a quadratic in standard form, which is the form y equals ax squared plus bx plus c. And from that, in the past, we've been able to gather based on A, what direction it opens, whether it's a stretch or a smoosh. Based off of A and B, we could figure out where the x-coordinate of the vertex was. We could find the y-coordinate of the vertex by plugging it in for x. And then we could also use C to figure out what the y-intercept was. Today we're going to talk about vertex form of a parabola, or of a quadratic. Which will look like this: y equals a parentheses x minus h all squared plus k. And vertex form, similar to, I guess, like slope-intercept form of the equation of a line, it will tell us a very valuable piece of information. Like slope-intercept form gives us the slope and the y-intercept. Vertex form gives us the quote-unquote slope of the parabola, as well as the vertex, which is going to be the most significant point on any parabola, right, is the point where it changes direction. So I want to open up Geometers Sketchpad, and I've got some graphs here for us to look at. And so here I've got the values of A, B, and C defined for this parabola in standard form. And when A is 1, or it's close to 1, cut me some slack. It's a regularly shaped parabola, right? So from the vertex it goes up 1 over 1, up 3 over 1, up 5 over 1, and that's how I can find some points and different things like that. And if I change the value of A, making it bigger than 1, or the absolute value bigger than 1, it gets narrower. If the absolute value is less than 1, it gets wider. And then eventually, actually that's an interesting case there, if A is 0, I just want to point out the whole quadratic term. Actually, that's funny. It's not exactly calculating that correctly. It must be rounding this. But the whole quadratic term would be 0, and I'd be left with bx plus c, which would be the equation of a line. And then when A is negative, it opened upside down and had similar features, right, of stretches and smooshes and stuff like that, right? So that was kind of what A affected on the parabola. The value of B is a little bit weirder. I find this kind of to be kind of a really bizarre motion that the graph does. But you can see that I've got some interesting effects there based off of B. In the current form, when B and C were both 0, I actually had a parabola with a vertex at the origin. But you can see I can actually have multiple x-intercepts. The vertex changes location and things like that. So B is a little bit harder to find out. B does help us figure out where the x-coordinate of the vertex was, the negative b over 2a formula. But I just think that this kind of has a really unique motion to it. And then the value of C is the vertical shift for us, which told us right here when C is 2.89, you can see the y-intercept is 2.89 as well. And one of the things I want to point out, let's see if I can actually zero these out again-ish. Close enough. And close. Better than close. Good. I just want to point out that A, graphically speaking, is also the quote-unquote slope between the vertex and the first kind of next point. I don't know. I don't have a good way to describe this point, but the next easiest point to find, I guess is the way I'd say it, on the graph, right? A is 1 here. A is 1 there. If A was 2, notice that going up 2 over 1 will give me my next point there. So one of the ways graphically I can read A is that way. So let's look at a graph of a parabola that's in vertex form. So A will actually have the same effect. So you can see A up 1 over 1. A is the 1 there. If this is 2.82, that means it's going up 2.82 over 1, and that's where it's crossing, right? And A affects, this A is exactly the same A of the previous one. When it's negative, it opens down. When it's between -1 and +1, it's a smoosh. When it's beyond those, it's a stretch. So all sorts of different things there. This is exactly the same a that we've seen before. And once again, I just want to point out, notice up 2 over 1, this 2 is the value of a. So if for some reason I was going from a graph and trying to write an equation, I would find the vertex, find my next closest, easiest point, and a would be the rise of the quote-unquote slope between those 2 points. Now let's figure out what h and k do here. Watch what happens here. When I change h, it appears as though h is having a horizontal shift influence on the graph, and that's exactly what it's doing. So when h is 1.9, x minus 1.9 parentheses squared would have been the equation there. Notice that my vertex is now at 1.9. Right? When h is -2, x minus -2 would be the same as x plus 2. So this h is actually kind of going, we'll see in some later examples that it's the opposite of the number with the x. My x-intercept is going to be at -2. And then let's figure out what k does. K appears to be a vertical shift. And even if h happens to be at 0 or 0-ish, oh good, I got it on 0, you can see that a in this case would be the y-intercept, right? 1.9, 1.9. But it's not always going to be the y-intercept. For instance, here I've got k is -1.27. That is definitely not the y-intercept. So this k is not equivalent to c in the standard form here. All right. There's some reasoning for that. Basically, if I'd expanded this binomial squared, it would have some quote-unquote c term of its own that it would be combined with k. Actually, I think the y-intercept ends up being whatever h squared plus k is, but that's definitely not a rule you should ever have to know. So it appears as though h represents the x-coordinate of the vertex, and k represents the y-coordinate of the vertex, right? So if h is 2, k is 3, notice my vertex is at 2, 3. And the vertex, like I said a moment ago, that's really going to be the most valuable point for us on parabola, right? So if I can find the vertex and I know the quote-unquote slope and direction that the graph opens, I really know everything I need about that parabola. I mean, sure, I don't know what the roots are, and sure, I don't know what the y-intercept is, but I can very quickly graph that in vertex form. So I just want to point out that a bigger than 0, this behaves all the same, right? The graph opens up. A is less than 0, opens down. I guess I got to write up there, don't I? The vertex is going to be at the point h comma k. And one of the things to be aware of is that it will be the opposite of the number with the x. All right, so if this is at x plus 3, my x-coordinate of the vertex will be -3. All right, so that's what that's going to tell us. And then a, like I said, stretching, smooshing, slopes is going to affect all of that the same way that we have had experience in the past with standard form. So let's do some examples here. So let's graph an equation y equals 2 parentheses x minus 1 all squared minus 3. So let's first figure out what are a, h, and k. So a is 2, h is going to be positive 1, it's the opposite of this number, and k is -3. So k actually is the same as that number. So something to be aware of there. So let's see, what do I know about this? I know that it opens up because a is positive. I know that it's a stretch by a factor of 2, right? Because a is, right, greater, the absolute value of a is greater than 1 is the way we described that earlier. I know that the vertex is going to be at 1, -3. So, and then I could find my slopes right? So normally I have up 1 over 1, up 3 over 1, up 5 over 1 are my slopes. What I'm going to do is multiply the numerators by a, right? So multiply all of just the numerators by a. So my new quote-unquote slopes will be up 2 over 1, up 6 over 1, and up 10 over 1. So let's graph this. I'm just going to draw one of my quick graphs. Let's see, the vertex is over 1, down 3, so I guess it kind of exists primarily here. So let's graph this. So over 1, down 3 is my vertex, and it opens up. So I do expect that this graph is going to have some x-intercepts. They won't have imaginary solutions when I plug in 0 for y. So here's my vertex, right? That's 1, negative 3. It opens up, and let's see, my slopes are up 2 over 1, so up 2 over 1 is right there. Right, 2 and 1. And then from this point, I could go up 6 over 1, so 1, 2, 3, 4, 5, 6. Actually, man, I didn't realize how well I planned that. That was unintentional. Gives me that point there. And now, if I want additional points, I know that my axis of symmetry is going to be... Actually, oh, that's one thing I could add. Axis of symmetry, AOS, is going to be the equation x equals whatever h is. In this case, it's 1. Right? X equals the x-coordinate of the vertex is that. And by the way, I think in earlier videos, I call the x-coordinate of the vertex v sub x and v sub y. That's really the same as hk in this case, just so you're aware. So I guess, yeah, the axis of symmetry, I'll add that to our little facts, is x equals whatever h is. So now that I have my axis of symmetry, this point is 1 unit away from the axis of symmetry, so I should mirror the other one over here, and there will be another point. This one is 2 units away from the axis of symmetry, so 2 units away over here would be another point, and then I'd be able to draw my parabola, something like this, and something like this. And even though I don't know where these x-intercepts are, I could get some estimates of where they were. And in this case, I happen to know where the y-intercept is. But I want to point out, negative 1 was not the k value. So k is not your y-intercept, typically. I mean, in some cases it will be, very rarely. It is the y-coordinate of your vertex. All right, so y-coordinate of your vertex right there. So that's how I could graph an equation when it's in this vertex form, right? So it's actually pretty quick, pretty fast that I could gather all of that information. So what about when a problem isn't in vertex form yet? Let's talk about how we can convert it to vertex form. So this actually takes a little bit of work. Let's see, I'll start with this problem here. What if I've got y equals negative x squared plus 24, let's see, x and then minus 60. So here's an equation in standard form. You guys could tell me a is negative 1, b is 24, c is negative 60. You could tell me it opens down, it's a regular shape. The y-intercept is negative 60. You could tell me all sorts of things, but let's actually write this in vertex form. So step 1, I guess if I'm going to try to give some steps to this, factor a out of, let's see, that's the variable a, of the first 2 terms. All right, so I'll show you what I mean by that. So a is the negative 1 here, so out of these first 2 terms, I'm going to factor a negative 1. And I'll have y equals negative 1, parentheses, x squared minus 24x. And now, behold, this blank, minus 60 blank that I've got here. All right, so those are hopefully foreshadowing of what our next step may be, which is complete the square. right? And I'm referring to completing the perfect square trinomial here, in which I'll find a new c term using the formula nu c is equal to b divided by 2 all squared, right, is my formula to figure that out. And this side here is going to be a little bit trickier. I'll show you what we do there. So to complete the square here, my new c is negative 24 divided by 2 all squared. So that's negative 12 all squared, which is equal to 144. Okay, so I'm going to, inside the parentheses, add 144. All right, completing the square. However, I can't just do that willy-nilly. That's changing what this problem is, right? So I have to do something that's going to make it equal to the original problem, right? So I'm not actually changing the way the graph looks, because that's no good if I'm switching forms and it's changing what my problem actually was. So check this out. Adding 144 in the world of parentheses was really subtracting 144. And you might have, in previous completing the square problem, solving a quadratic by completing the square, you'd have said, okay, so that means I want to subtract 144 from the other side of the equal sign, right? So this y would have still been positive, and I would have done that. However, I don't want to have the equation y minus 144 equals blah, 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 or negative 144 plus y equals blah, 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 because that's not going to be helpful. I want this equation solved for y. So instead of subtracting 144 from over here, I'm going to just do the opposite of what this effect was right here. So I'm going to add 144 here. And let's see, so to find this number, this is what you do. I guess I could write a little formula for it. It will always be subtracting a times your new c. All right? So negative of negative 1 times 144. And the double negative became positive. All right? And what that's doing is just making sure that this effect here was accounted for so that I wasn't changing what I originally had. All right? And then I think step 3, I guess I could, I'll make that its own step. Add outside parentheses the following, where negative a times new c. All right. I guess I'll call that new c there. I could call it c prime maybe. That's a very math thing to do. And then my last step will be fast factor. Right? So, so I'll have y equals negative 1 times. This whole set of parentheses here is a perfect square trinomial, which fast factors to something all squared, and that something will be x, and then minus 12 all squared. All right. So that's based off of this pattern here, the fact that a squared plus or minus 2ab plus b squared is equal to a plus or minus b all squared. That's the pattern that I'm using there. And a bunch of little formulas showing up on this, but it's really not terrible. And then let's see, I can simplify this right-hand side. Negative 60 plus 144, what's that? Plus 84. So here I go. Now I've got my equation in vertex form, and I could then tell you, that a is negative 1, and I could tell you that the vertex is positive 12, 84, recalling that it's the opposite of that number, right? Opposite. Right, and then you could even graph and do everything from there. So this is a little bit tricky. I think I'll do maybe one more example like that. Oh, we're already at 20 minutes. Yikes. Well, if you need an additional example, I'll give you one. Otherwise, feel free to stop watching anytime. Let's see. So example. Let's give you the equation. Actually, I'll use f of x just to get us used to that notation as well. What if f of x is equal to 3x squared minus, let's say, 18x, and let's say plus 10, something like that. All right, so step 1, I'll factor a out of the first two terms. So f of x equals 3 parentheses x squared, 3 out of 18 is 6, blank, plus 10, blank, right? Complete the square, so my new c term is going to be negative 6 divided by 2, all squared, negative 3, all squared, positive 9, added 9 in the world of parentheses. Now in the world of the problem, I really added 27. So to balance that out, since I'm all on the same side of the equal sign here, right, I have to subtract a 27 as well, right? And now I can fast factor, and I'll get f of x equals 3, parentheses, x minus 3 all squared. This minus 3 you could find right there. You also could find it by dividing your b term by 2, right? Whichever way is easiest. And then 10 minus 27 is negative 17. So here it is in vertex form. And you could tell me that a is 3, it opens up, it's a stretch, and that the vertex is at positive 3, comma, negative 17. Right? So it's actually a really wonderful, simple, easy sort of thing to do. I think the trickiest thing is this completing the square part. Right? But it's not all that bad. Thank you for watching, and I will see you guys next time.